This is LeetCode 155 min stack. For this problem, we are going to design a stack that supports push, pop, top, and retrieving the minimum element in constant time. To implement the minStack class, we're going to implement the following functions: minStack, which initializes the stack object; push, which pushes the element val onto the stack; pop, which removes the element on top of the stack; top, which gets the top element of the stack; and getMin, which retrieves the minimum element in the stack. So this problem has the following constraints. The elements we are adding to the stack are between -2 to the 31 and 2 to the 31 minus 1. The methods pop, top, and getMin will always be called on non-empty stacks, and at most 3 times 10 to the 4 calls will be made to push, pop, top, and getMin. We can already push, pop, and get the top element of a stack in constant time. For example, suppose we have a stack with the elements 3, 1, and 2 on it. To push or add an element to the top of the stack takes constant time. To pop or remove the top element from the stack also takes constant time. And to get the top element of the stack also only takes constant time. Where this problem gets tricky is retrieving the minimum element in the stack in constant time. So in a regular stack, we would have to iterate through all the elements in order to find the minimum, which is an O of an operation. So how would we find the minimum in constant time? Well, we can get the top element of a stack in constant time. So why don't we just put the minimum of the stack at the top? And let me add another element here. So now retrieving the minimum element is an O of 1 operation, constant time. But what if we were to remove the top of the stack? Well, in order to find the minimum, we would have to iterate through all the elements again, which brings us back to O of n. So instead of just putting the minimum at the very top, we should put it at every level. That way, even if we were to remove the top element, we would still be able to find the minimum element in constant time. So now for every element in our stack, instead of just having a value, we'll also keep track of the minimum element in the stack at that level. Let's see what that looks like in code. To represent this concept in code, we are going to create a class called element with 2 properties, val and min. We're going to create a constructor for the class. As well as getters for val and min. So next we're going to implement the code for minStack. So first we need a stack to represent our primary data structure, and inside of the minStack constructor we're going to initialize our stack. Next is push. So there are 2 cases to consider, right? One, if the stack is empty, and one if the stack has elements on it. So if the stack is empty, stack is, has 1 or more elements or is not empty. So if the stack is empty, then let's say we want to add element 3 onto it, right? Then the minimum of the stack would also be 3. So it's whatever the value is, this value here. So stack.push, right? We're saying that the value of the element is val, obviously, and we're saying the minimum of the stack at this level is also val. So next, what if the stack has 1 or more elements on it? Well, we'd have to compare the value to the current minimum, right? So let's have a variable to represent the current minimum of the stack, which is stack dot peak. So peak would get us this entire thing, but we only want the minimum. So it'd be peak.getMin. Next, we have to compare val to min, the current min, right? So what if val were less than the current minimum? All right, so the current minimum right now is 3. So let's say the value is 1. Okay, so we already have that. Then the minimum would now become 1, right? Would become val. So if val is less than current min, then stack.push new element current min, or sorry, val. I noticed a typo, so my bad. So next, what if val were equal to current min? So current min is 3. What if value were 3? Now the min would stay the same, right? And what if the val were greater than current min? So for example, 5. 5 is greater than 3. If we were to add 5 onto the stack, then the min would stay the same as well. So we really have to account for two cases, right? One is if val becomes new min and min stays the same. And by min here we mean, yeah, let me just clarify, minimum of the stack. Minimum element in stack stays the same. So let me erase all this so you can see this better. So stack.push new element val current min. Okay. So pop is just removing the top element from the stack. So if you remember in our constraints, we're never going to call pop on an empty stack. So we don't have to worry about checking for nulls or anything. But let's say you're asked, to account for that in an interview, then you would just put something like if stack is not empty, then pop or remove the top element. So top, which is to get the top element, we would do something similar. Return stack.peak. Stack.peak would get us, again, this entire thing, and we only want the value, right? So get val. And for get min, we return stack.peak. Now we want this value again, right? Something similar to what we did here. So stack.peak.getMin. Okay, so and again, if you're asked, in the interview to account for null or if the stack is empty, then you put like if conditions to check. So next, let's run the code and see how we do. Okay, great. So hope you enjoyed the video.